Hi there, Luke McKinney, Prep 101's Physics 101 instructor, and in this video we'll be doing projectile motion, a very common example of the equations of motion in two dimensions.
Now, projectile motion comes up all the time, and that's brilliant for you because it's basically double marks, because it's doing equations of motion all over again. The difference is equations of motion is in one dimension. Projectile motion uses two dimensions, but each of them is separate. So we're basically getting double marks for doing the same thing twice. Now, the basic idea of projectile motion, you have something, you launch it at some launch velocity at an angle, and then it flies in a parabola through the air until it hits the ground or something else. Now, young people are all very used to this with Angry Birds, but of course, us older, wiser people like me are used to it from Worms, which was a much better game a long time ago. But either way, we deal with this shape, the parabola, and there's a couple of properties about it which are useful. The first is that it's symmetric. So it takes just as long to go up as it does to go down. So if it takes 10 seconds to rise that height, it'll take 10 seconds to fall down. It's also symmetric if the launch speed at this point was 20 meters per second, then at the same height over here, the speed would again be 20 meters per second. And a little bit of revision, you can see that's the same speed, the same size of number, but it's a different velocity because it's a different vector, a different direction. It's going down instead of up. And another little useful property we'll use later, at the top there, the vertical velocity for an instant is 0 meters per second because it's not going up or down anymore. It was going up before, which is in the plus y direction. It's going down afterwards in the minus y direction because in physics, plus and minus are just directions. And we're going to plug all of these into the equations of motion. Now, how do we do that? Well, we look at it again. Remember, if you try to do two things on one diagram, you don't get anything much done. The key is when this is going in two dimensions, we have the x dimension horizontally and the y dimension vertically. And the key is there is no acceleration usually in the x dimension, unless they mention something like the projectile has a rocket motor or something, and you wouldn't miss that. In the y dimension, the acceleration is minus g. So it's minus 9.8 meters per second squared. So for our object flying through the air, it always has an acceleration down of minus g, so that's minus 9.8 meters per second squared. And we'll see now how to fit that into our equations of motion. The first thing we do is break the problem up into our two dimensions, x and y. We've got an object with a launch velocity at some angle to the horizontal. And we can break that up into x and y using trigonometry, which sounds like a very long word, but something we'll use a lot in this course. We'll turn it up later in forces and momentum and all sorts of stuff. We just have our right triangle. The horizontal component is the velocity times the cosine of the angle. And the vertical component, the launch vertical component, is the launch velocity times the sine of the angle. And those are the values that we use for our equations of motion. Now you'll notice again what I did there. I said the launch horizontal component is the launch velocity times the cosine of the angle. I didn't say Vox equals V0 cos theta, because that sounds like a serial number or some sort of override code, which isn't really how our brains work. So always remember to say the letters as we move on. And now we'll plug those in to the equation. So let's plug these into the equations of motion. We start with the horizontal component. The horizontal velocity is the old horizontal velocity at launch plus the horizontal acceleration times time. But we know there isn't any horizontal acceleration. So that's just the launch horizontal component. and that doesn't change through the problem. But you still write that equation out the first time each time, because if it's a long answer question, you'll get the marks. And if the question does do anything blatant, like say there's a horizontal rocket booster giving an acceleration of 1, you'd go, oh, cool. I plugged the acceleration of 1 in there. Now, what we usually want to work out in a problem like this is how far something has gone. So we use the next equation. The new horizontal position is the old position plus the launch velocity times time plus a half the acceleration times time squared. Again, the horizontal acceleration is 0. So you plug in the numbers and you can find the new position. And you find what we need is the time. Now, this is a classic thing in physics. You've got an equation, but you've got more than one unknown. You need to find a new value. You always just need a new equation. And well, we're dealing with x and y, and we've already used x. There's only one more equation to look at, y. Now we can see how it'll work. If I launch a projectile, when it's gone as far as it can, it's hit the ground. So I knew its new height is 0. Or if it's hit some platform, let's say we want to know when it lands on a 10-meter tall platform, that means at that point, its new position is 10. So we plug that into the same equation of motion for y. The new height is the launch height plus the launch vertical component times time plus a half the vertical acceleration times time squared. So you plug in the values. The new height is the old height. The launch vertical velocity component plus a half minus 9.8 times squared. And you get an equation for time. You plug in the numbers, you solve the equation for time, and then you tick that and you can plug it back in and find whatever you want, which works out nicely there. There's also another equation that can turn out very useful for this. A common question on this is we can be asked, what is the maximum height of the projectile? So when it's gone as high as it can, what's this height here? And we could do that through the first two equations of motion, and it would work. We'd eventually get there. But we know something about this top of the projectile motion. Remember, whenever you're doing equations of motion, some of the numbers are given as numbers and others are given as words. And we've already seen at the highest point, that's a number. The new vertical velocity is 0. So we've got a velocity and we only care about a distance. We don't care about time. And that might cause some bells to ring from the equations of motion primer. Remember, we have an equation for that. The new vertical velocity squared minus the old vertical velocity squared is twice the acceleration times the change in height. Or some people like to write it the other way around. They move the launch velocity across the equal sign. You can see it's exactly the same whichever way you prepare to do it. So what we do is we plug in the values. We know the new vertical velocity at the top is 0. We've got the launch velocity from the problem, vertical component, is equal to twice the vertical acceleration of minus 9.8. The new position is the height, minus the launch height is 0. And then it's that beautiful thing we hit so often, plug and chug. We can find the answer in just one step after doing a bit of that. One other little novelty about projectile motion, how do you launch to go as far as possible? You want to get the maximum range here. Well, with no air resistance, and in these problems there aren't air resistance, that's a much heavier engineering idea, you'll always get the maximum range at 45 degrees launch angle. It's the best balance between horizontal speed and air time. Just a quick little novelty, but it's been asked on occasion, so I always make sure everyone knows it off the top of their head.
I hope that was useful. There's plenty more useful videos in the playlist and even more useful exam style practice and tips and all sorts of things in the prep sessions. So make sure you join the Prep 101 Facebook Study Hub. You'll find out about everything we're doing there, when the prep sessions are on, and there's even sometimes free ones, so you don't want to miss those. Hope I'll see you there.